Hello, and welcome to my presentation on Lab 6 about magnetic molasses. So here's a brief introduction to the lab. The purpose of the lab was to compare the experimental time it takes for a bar magnet to fall through a tube of aluminum foil while calculating the simulated time via a computational model and also experimentally via a stopwatch. So preliminarily, here are the results that we found. The average experimental time taken to fall through that tube was 1.17 seconds, but the expected computational time was 1.42 seconds. So here are the fundamental principles involved with the lab. We have, first of all, the Biot-Savart law. Right there you can see. It describes how a current element creates a magnetic field, and it depends on current, distance, and direction. Faraday's law is also important, which allows us to calculate the EMF, as you can see down there with the equation there, with d phi over dt. And we also have Newton's second law, which we all know and love, which is F equals mass times acceleration, as well as Newton's third law, which states that each force has an equal and opposite reactive force. So here's a procedure for the lab. First we start the recording, then drop the bar magnet through the tube of aluminum foil. We repeat this 5 times to get an average, and then we watch the video to find the timestamps of when the magnet entered and exited the tube. And once we do that, we calculate the average time spent by the magnet inside the tube. So here are the initial conditions as shown. All those measurements there are pertinent for finding the results later. And that was on the right. You can see the exact aluminum foil that we used. In my lab, our partner there is holding the magnet before she puts it in. So here are the system and surroundings. The system was a bar magnet and the surroundings was everything else. So here's a computational model that was used. As we can see right there, the equation at the top is the Biot-Savart law being implemented into the code. And then further down there, the equation there in the middle shows how magnetic flux was calculated from the code. And then finally down there on the bottom, that is how the force on the ring was calculated. And here is the graph exactly of the computational model of what was expected. So the velocity was going faster before it entered the tube. Then when it was in the tube, it was expected to remain at a constant velocity. And then as it exited the tube, the velocity would pick up once more. So some similarities and differences between the data and the model predictions. Well, the computational model expected the magnet to be in the tube for longer than what we found experimentally. So that was the main difference between those two methods. So some assumptions made. Well, we assume negligible air resistance. We also assume a uniformly distributed aluminum foil around that tube, as well as the induced magnetic field being what actually affected the magnet's motion. So some possible sources of error. Well, other magnetic fields could have been present. Some errors possibly from measurements. Also, air resistance was not accounted for in the computational model. Furthermore, friction from the walls of the aluminum foil could have produced some error as well. So what if the resistivity of the conductor were reduced as close to as possible to zero? How would this change the dynamics of the falling magnet? So, well, this would imply actually a very small resistance and therefore a very large current. So this would increase the magnetic force and make the magnet fall very slowly through the tube. So the experimental time would be larger. So what if holes or slots were cut into the tube? How would this affect the ring currents in the model? Well, if this was done, the induced current would be disrupted and decreased. This would reduce the magnetic force on the magnet, which would allow it to fall more quickly through the tube. So we would see in the data that there would be more seconds in which that magnet would be spinning in the tube. So that was what would happen for that scenario. And thank you for your time.